about multi-timescale world models. The talk will introduce the paper Multi-Timescale World Models, which was accepted recently in Neurips 2023 at the Spotlight. Intelligent agents use internal world models to reason and make predictions about different courses of their actions at many scales. And Vaisakh is pursuing his PhD in robotic learning under Prof. Gerhard Neumann at the ALR lab. He finished his master's from the Indian Institute of Space and Science Technology. His PhD focuses on building probabilistic recurrent state space models and learning world models with it. His research interests are in developing algorithms that can learn continually in a non-stationary environment and can solve long horizon tasks. Vaisakh, take it away.
Okay, thank you for the introduction. So hi, everyone. I think it's good morning there, so good morning. My name is Vaisakh, and I'll be talking about this paper that was recently accepted at Neurips called Multi-Timescale World Models. So these are some of the co-authors. So Saleh is also a fellow PhD student. He's also funded by SAP in Germany. Louis and Olsen are research scientists at Bosch. And Professor Neumann is my advisor. So maybe I'll just also briefly introduce where I come from. So like this is our research lab. I am advised by Professor Neumann, and these are some of the wonderful colleagues I've been working with over the last 3 to 4 years. Okay, so what is the scope of this talk today? So I would be talking about why should one learn world models and why should one make it multi-timescale or hierarchical? And can we formalize such multi-timescale world models probabilistically? And if we can formalize it probabilistically, can you perform inference and learning in such a system? And are they effective in very long horizon hierarchical predictions that can extend up to several seconds? So these are some of the things that you will hear in this talk. So world models, what are they? So they are a model or a simulation of, it can be biological or artificial, of the world that we live in. And what it does is it predicts the next states of the world as a function of the current state and actions. So it's just a prediction machine of the future, what is going to happen in the future given some actions. So this is a very simple way of representing a world model. And as I mentioned, you're predicting into the future what the states are given a set of action. Okay, so I'll also maybe motivate why should one care about building world models. So many of this motivation is from this paper from Jan LeCun. So most of the motivation is are the stuff that I found convincing from his paper. So as you know, like there is a world model in our human brain somewhere in the prefrontal cortex, so which is a good motivation to learn it. So according to Professor LeCun, there what we call as common sense is a collection of mental models, which tells the agent what is likely, what is plausible, what is impossible, and things like that. It can be used to reason, plan, explore, and imagine new solutions to problems. And it's well known that model-based methods are much more data efficient than model-free alternatives. So yes. So how is the world model in recent literature? So this is a very simple way in which the world is modeled right now, this probabilistic graphical model. I have omitted actions for brevity, but you can also include actions. And so it consists of a set of latent states. And these latent states have an inherent transition dynamics. And these states creates some observations, as you can see here. And based on the assumptions in this latency, if it's a discrete latent state, people call it as hidden Markov models in literature. If it's continuous latent states, people call it state space models. And if the deterministic variants of this, like LSTMs, GRUs, etc. So I'm going to focus more on continuous latent state models or state space models, because these are extensively used in recent literature for world models. And also, I'm going to talk more about robotic space dynamical system, which is more continuous. So I'll be talking about state space models in general. But a fun fact out there, if this random variables are Gaussian, and if you can perform exact inference on this is what we call as a Kalman filter. So just putting it out there. Maybe some more motivation. So this is also a slide from Professor Eriksson's lecture on graphical models, where he says, yeah, there is a Kalman filter somewhere inside our brain, and maybe it's very simplified, but still he thinks maybe something similar to a Kalman filter exists, which models the world in our human brain. Okay, so again, how is world model in recent literature? What people use is something called deep state space models or recurrent state space model, which combines the best of both worlds. That is probabilistic inference and deep learning. Why should you care about probabilistic, these models being probabilistic? Because our world is inherently stochastic, it's not deterministic. So modeling distributions is nice. The structure of these neural networks are inspired by this probabilistic state estimator, and learning happens via backpropagation through time. There are several world model variants in literature. So some of them use exact inference. So the backprop Kalman filter, or some of the work from our own lab, recurrent Kalman networks, hidden parameter, RSSM, which is sort of meta-learning Kalman filters. This use exact inference scheme on this state space models for inference. There's variational inference-based state space models, and the popular Dreamer series of models perform variational inference on this state space models, and then you can model the world like that as well. Okay, so what is the problem with existing world models? So existing deep world models focus on predicting or dreaming at a single time scale, and mostly they are good at short-term predictions. So the single time scale is often in the range of milliseconds. So they use time scales of the range of milliseconds. But as humans, we have the ability to predict, plan, and reason at multiple levels of temporal or spatial abstractions. So for example, if I want to move from Germany to Canada, I won't think in terms of every single muscle action, so movements I should take in the next throughout this travel. I rather would start thinking more abstractly, like, okay, I have to start from my home, go to the next tram station, from there go to the railway station, then go to the airport, then catch a plane, and things like that. So it's more abstract. And then once I've set these abstract goals, then I go to a much lower level abstraction. And finally, I think about what muscle movements or what small actions should I take to reason or plan. So this is important for long horizon predictions and planning. So can we have models that have this idea? So is there a way in which this can be modeled, modeling the world at multiple temporal abstractions? So what you need is, you need a world model that can predict or dream at multiple temporal abstractions. So there's one with there's a fast time scale, there is a slow time scale, and then maybe super slow time scale. And this higher level abstractions are slow, and they usually take care of long-term trends, but they don't care too much about the very minute details in our world. But they rather take care of abstract level long-term trends. But maybe the fast ones, the lowest one, focuses on short-term trends and takes care of very minute details that you should take care of, something like that. So so this is one way to maybe model the world. So this is what we try to address in this paper. Can we formalize such a model probabilistically? And then that's when we propose this probabilistic graphical model called multi-time scale state space model. And yeah, it may look a little bit complicated, but I'll try to break it down, what exactly is happening here. I'll start with two hierarchies. There are only two abstractions, but a general definition for this would be, we will see it later. So it has a fast time scale state space model operating at a time scale of delta t. Then there is a slow time scale state space model with its own dynamics, operating at a time scale of h times delta t. So this factor h is important, which would come later on in the talk as well. And they operate on abstract states and actions. And I will also define what these abstractions are. And finally, the most importantly, how are these connected? The upper level time abstract latent states reconfigure the lower level latent states for a certain time window of h time steps. And after h time steps, the task changes, something like this. So this is how we defined this MTS3 or multi-time scale state space model. Okay, so what are these abstractions that I was talking about? How do you infer these abstractions in these models? So abstractions in reinforcement learning is a very large research area itself with multiple open problems. And how we chose to define this as fusion or aggregation or compression of a set of H observation that you observed in a set time window into a single latent representation. So to give some intuitions, like let's say, in a certain time window, you had a set of observations that you saw here, and you want to get a fused representation or a mapping to a single vector, which is the abstraction for these guys observed in that time window. So how do we achieve this? We achieve this probabilistically based on that graphical model using Bayesian conditioning of a set of observations. So what is happening is, let's say these guys, these observations there are H observations here. So these are represented by this are t is equal to 1 to H for a time window K, but you can ignore it. And we assume that these guys are created by a latent variable L. And what we want to calculate is the posterior probability of L given a set of these observations, which is basically a Gaussian conditioning operation. And because of the Gaussian assumptions, we can get a closed form solution for this. And this is encoded as a layer in the neural network. So these equations. So that's how we define our abstraction. And okay, so since it's Bayesian, we have a prior. And what should this prior be? So this prior can be assumed to be uninformative, like a zero mean unit variance prior. But we have some prior information from the previous abstract time step, right? So you use that, like the prediction from the previous time step is used as the prior here. So we use an informative prior. So this is how you get this state abstraction or the tasks. And we follow a similar procedure for getting action abstraction, which is defined as an aggregation of a set of primitive actions. So this is the same way in which you define the state abstractions. So how is it implemented? So this is how the network looks like when you actually implement it. So you have a set of H observations that you observed in a time window. You put some temporal embedding, just like in transformer architectures. You pass it through an encoder, and you get a set of H encodings for this one and corresponding variances. And then you pass it through these equations that I mentioned that perform Gaussian conditioning, and you get a posterior over the abstract states. So this is how we get the abstractions. And these have some really nice properties. So as I mentioned, these are closed form equations, like derived from first principles. These are permutation invariant, which means you can parallelize this operation. So you don't have to do any sequential stuff. You can just effectively parallelize, and it's fast. And it's order of H time complexity. It's sort of a deep set encoder, and similar deep set encoders in transformer architectures like self-attention have order of H squared complexity, but it just have order of H time complexity, or the number of observation time complexity. Okay, so as I mentioned, it's implemented as a deep set encoder, and I'll also try to give two interpretation. Okay, I see a raised hand. Yes, please.
Hi. Yeah, so do you not care about the denominator? The probability of the R1 to H?
This
Or
one.
you just use it as a normalizing factor? You don't have to worry about it.
That's what. Yes, that's a good question. So that's what I mentioned. Since we have Gaussian assumptions, you can get this in closed form. You can derive it in closed form. You don't have to for Gaussian and linear assumptions. So there are formulas for this. So this prior is Gaussian. This likelihood is Gaussian. If that is the case, then you can have a closed. It's based on completing the squares and things like that. So you can effectively solve it in as a closed form equation. But under the condition, everything is Gaussian and the observation model is linear.
It's basically a common filter, is it not?
Exactly.
Yeah, okay.
And that's what I was about to tell you.
Okay.
Like, not Kalman filter, but Kalman fusion, maybe.
Okay, cool. Thanks.
Yeah. So that's what I'm gonna say. So some interpretation for this is can be thought of as a probabilistic attention, which means like the variances encode this attention weight, and it's sort of a weighted mean over these encodings, and this attention mechanism is like learned through these variances. It can also be thought of as a parallelized Kalman fusion operation. So we can also think of it as in that way. So that's how we infer the abstractions. Okay, so how does the learning happen? So this is the architecture for a 2-level MTS3. You have a fast time scale, and you have one cell, fast cell, and a slow cell. And this is the abstract level hidden state, and this is the fast hidden state dynamics. And learning happens through a single training objective. There's just one training objective, which is the predictive marginal log likelihood at the lowest level. And then you can train it end to end for all the hierarchies, irrespective of the number of hierarchies. And training is also happens via self-supervised learning, which means that we are tasking the network to fill in missing observations. So which is very, very important to get good results. If you don't do this, you don't get any nice results. So this is another, so some ways in which we do the training. Okay, so how do we perform hierarchical inference in this network? So we now dream at 2 levels. First is the abstract level, which predicts the tasks that you have to do. Then once you have this task or higher level of abstractions or latent state representations, now you use this to make predictions for the lower level. So what is happening is it's a task conditional prediction for the lower levels. Then the task changes after each time step. Again, you predict something like this. So this is how we perform hierarchical inference. Okay, so we have a very formal definition for extending this to an arbitrary number of hierarchies. Please. Yes, please, Liam.
Oh, sorry to interrupt again. So is it a limitation that you have to assume this like fixed H time steps for each higher level?
Yes, it
like
may be.
task?
Yes, maybe it is a limitation. So I think in hierarchical reinforcement learning, there are 2 ways in which people usually solve this problem. One is this option framework where they don't have this fixed time. We can essentially have adaptive time scales or temporal abstractions. Then there is this set of algorithms called feudal reinforcement learning, where you have this edge time stuff. So we follow this approach, sort of a feudal way of modeling this world. So
is there some kind of hack you can do if it doesn't actually take H time steps to complete a task, like that you can, in some sense, like pad the trajectory with a 0 action or something so that it like fills out to be H? Or in practice you need it to be exactly like H proper action?
So H, how we choose H is sort of, so right now we only focus on predictions, not solving control problems, one thing.
Okay.
So it's just predictions. And H is a very important hyperparameter. And I will talk about this, how varying this value of H affect the predictions. So
Okay.
Yeah, so
Thanks.
maybe you will have more questions in that slide. Okay. So yeah, let's move on to the experiments. I perform experiments mostly with predictions on real and simulated robots or agents. We right now focus only on proprioceptive observations, that is joint states and angles. But still, we want to make it more difficult. So we create a scenario of partial observability where only the joint positions are given and we mask out the velocities and the latent state has to infer it over time. So it's a tricky scenario. It's a difficult problem. Okay, so first question that we try to answer is, can this formulation make accurate long-term mean predictions? So we took two kinds of dynamics. One is a real excavator, this is from Bosch, with non-Markovian dynamics because it's a hydraulic actuator. So there's a hysteresis associated with it. So it's a very tricky dynamics to model. And the second one is a non-stationary dynamics, in the sense that this robot is traversing terrain with varying slopes. So then the dynamics is changing, which is also very tricky to model. So let's see how we perform. So MTS3 is this red one. For these two data, the only two models that can compete with us are the transformer variants, which is the autoregressive transformer, which is in this violet stuff, and the blue one is a multi-step transform, which is right now people use that a lot in time series forecasting literature with transformers. So yes, we are very, very good at modeling this dynamics, this tricky dynamics. And again, these are continuous systems. We also perform some experiments on commonly used benchmarks from D4RL. We just use the data set, and again, partially observable, only positions. Here again, we see that most models perform decently, I should say, but the best prediction error is still mostly with MTSC, or we at least compete with transformers, or in some cases outperform it as well. So yes, so what are the reasons? Why might it be so? So I will show you some ablations why it might be so, like in my opinion. Okay, but we also tried to answer another question: can we make accurate long-term probabilistic predictions or variance estimates? Because we have a probabilistic model, so it should be good at modeling uncertainties. And yes, Liam.
Yeah, sorry, I was just wondering about, especially the robot experiments, is the ground truth dynamics stochastic or deterministic? Like, is there actually a lower bound on the possible performance, RMSE performance that you could get in terms of like in a probabilistic sense?
I haven't really thought about that. So what do you mean by like stochastic deterministic?
Like is there a way that you could drive this RMSE all the way down to zero? Like over time? Like if you had perfect information, could you get it to go to zero? Right?
I don't know. So I have to think about it. I don't know if we can do that. Like, so what perfect information? Like, if you have a perfect dynamics model, you mean, or?
Yeah, exactly. Like, because is the stochasticity in the system going to prevent you from ever being able to, at least in the probabilistic sense, have a perfect prediction?
Maybe in some of this, for example, I think in this maze, I think there is some multimodality there, so it can go either here or this way, something like that. So then this is the place where we get the worst performance for all the models, because it's really tricky. And maybe there is some multimodal behavior there, which is stochastic, as you mentioned, and it's not possible to get perfect predictions. So I didn't make a proper analysis of that, but I do think this is a very tricky such scenario.
I'm curious, did you try on the quadruped for the maze? Like in D4L, they also have like a ant running around.
No, I didn't try that, or maybe I did try that, but yeah, I think these were the first three stuff that we tried out, and then later on I didn't invest a lot of time into that. But why do you think so? Well, like why were you interested in that?
Because that one, it's very, I guess, it's a lot more,
Stochastic.
yeah, there's more stochasticity and it would benefit a lot from long-term prediction where
Yep.
yeah,
So
these
I
are
think this is one drop.
more has more modes.
Okay. So I think this is one place where this model might fail because it can't maybe model multimodal predictions or something like that, because we have unimodal Gaussian assumptions. So this is also something you have to think about because our world is also multimodal. So yes, so you're right. That's a very important problem statement to consider. Okay. So yes, when coming back to the variance or uncertainty estimates, yes, we are a probabilistic model. So it was not very surprising that we are good compared to this deterministic models like transformers or LSTMs or GRUs when it comes to variance estimation. These deep Kalman models that I talked about, like Kalman networks, recurrent Kalman networks, hidden parameter, recurrent Kalman networks, and these sort of things, they are probabilistic models, but they can't model very long horizon stuff. So their means are also very bad. So we don't care about it. Was the variances, we don't care about it. It was really bad. But still, I think there is a lot of room for improvement. So it can be even much better calibrated. But so I would say it captures the variances reasonably well. But capturing uncertainties in dynamics models are very important because, but in the context of model-based control and planning, or even offline model-based methods where you have to be conservative and things like that. So this uncertainty information can be important. So further analysis need to be done on how to improve this uncertainty estimates and make it more better calibrated. So what is actually happening? So this is a very hand-picked one, like one of the best trajectories from this hydraulic excavator data set. And as you can see, this is like an autoregressive transformer, which has this autoregression, and autoregression is not really good for multiple, because error accumulation can happen. So yes, it's not so good. LSTM completely breaks after one or two steps, and like we are like very, very, very good. So what is the reason? Is it too good to be true? So we try to make some further analysis. So we try to make an ablation on this time scale parameter h that I mentioned before. What happens when we change this h? So a higher h means a slower time scale for the task dynamics, which means we are talking about a much larger abstraction. And what we observed was when the h is very small, it's like very fast task dynamics, then it was deviating. Like these are MTS3 variants with different values of h. It was completely deviating. For h is equal to 3, like it was okayish. We reported the result with h is equal to 30 because it gives the best RMSE error. And this was h is equal to 75. And here you can notice something very interesting, which is this jump sort of a behavior happening after every h time steps. And what is happening is the higher level latent state changes, and it is grounding the prediction back to the accurate domain. So this here it's like after every 30 time step, you can notice this grounding happening here after 75 time step. But in this case, the lower level guy has to make a much longer prediction. So maybe that's the reason we have this sort of a behavior. But again, here more analysis need to be made. But we also performed ablation with different values of h. It's like 2, 3, 5, 10. It keeps on improving. At 30, we get the best performance, which is what we report in the paper. And as we increase h further, then it starts going up again. So yeah, this is, which kind of shows that this time scale, multi-time scale learning is important for accurate long-term predictions. Okay, so we have code and implementations, but it's not released yet. It will be released in a week or something like that. But there is something very interesting here as far as implementation is concerned. All you need here for making arbitrary number of hierarchies is two Gaussian transformations. So as Liam was mentioning, it's basically Kalman filter operations in variations of Kalman filter operations. So if you think about the forward pass of the model, what is happening is so in the higher level, there is this Kalman fusion over a set of observations. So it's update, then predict, update, predict, update. Then there is this update at lower level, predict, which is a task conditional predict, update, predict, update. It goes on like this. So this update step is the green one, and observation update and predict step is the orange one. And this can be thought of as two Gaussian operation. One is a Gaussian conditioning and one is a Gaussian marginalization. So you can encode, all you need is just two layers, a Gaussian conditioning layer and a Gaussian marginalization layer. And then you can just use this plugin, and create arbitrary number of hierarchies. So maybe I can just quickly go to the implementation, which would be online in a couple of days. But here we mentioned that the two building blocks, so these predict steps and this update steps are instances of marginalization and conditioning. So all you need is this building blocks, which is Gaussian transformations, a Gaussian conditioning layer and a Gaussian marginalization layer. And in the implementation, we have these two generic layers, and that you can use this and get creative and create more new architectures. It need not be the same one that we mentioned in the paper. So it's and also add more hierarchies and things like that. So yes, and okay, so we had a question during the reviews, like why should we care about this when we have models like transformers? So some of the answers that I think is the reason that this is also an alternative is the state-space models are more natural for modeling continuous dynamical system, and transformers were designed for discrete dynamical systems, or like NLP sort of tasks. So that's one reason. The second thing is we combine the benefit of both worlds. First is we have this deep set-based encoders to capture this context or global trends, just like self-attention in transformers. But we also enforce causality by design. So it's just like RNNs. There is this causal inductive bias given, which I don't know if transformers are capable of drawing or concluding from data. And also this is a formalism, or a way of probabilistic formalism, or a way of thinking about learning world models at temporal abstraction, and implementation on how to do this can vary. So just like an MDP or state space model, we have proposing kind of a formalism, but how you perform inference and implementation on this can vary. And maybe you can use transformer-based encoders or something like that. Okay, so in conclusion, we proposed a formalism for learning world models at multiple temporal abstractions. As a principal sequential latent variable model that can capture the stochastic nature of our environment, but with some star mark, maybe not multimodality. And it can produce accurate long horizon predictions and uncertainty estimates. And some of the future work can be how to perform hierarchical planning with this model. Can we do that? How to do that? So right now, we only focus on prediction. Right now, we perform inference as exact inference. We can also try variational inference on the same state space model, just like dream a series of models, and include nonlinearity in this latent space and stuff like that. So this can also be another alternative. Include more hierarchies and see what happens when we have very long horizon predictions, say to 10,000 time steps or something like that. But yes, and also we use proprioceptive data. So what happens when you use image-based models? Then currently we have a reconstruction-based loss. So should we avoid this reconstruction-based loss and things like that? Okay, so that's it. Thank you. Thank you for your attention.
Hi, can I ask a question?
Sure.
So, like, I guess what I'm trying to wrap my head around is like intuitively how to interpret these abstract states. It's like in something like an options framework, right? Like it's kind of a clear interpretation of what that option is supposed to be, like in terms of like the sort of hierarchy of the way that you're doing planning, I guess. But in some of the examples that you showed, I wouldn't necessarily say that it seems to adhere to this kind of like hierarchical setup where there is some kind of like true underlying abstract state that if we can infer it, it actually it would that we should condition the dynamics on some kind of like abstract state like this. I'm not sure if I'm making any sense, but like it seemed more or less like it was just like one dynamics model that's rolling out in some of the examples anyways over like a long time period. So I guess what I'm wondering is like, do you have some intuition like in those particular, like, and I guess you gave some intuition, but like in those particular cases, what is being represented by that latent state? And like,
Yes, so yeah, this is some study we have to do, like make some intuitions or make it more explainable as to what exactly is being encoded or learned here.
mm-hmm.
I think it also depends on the loss function we use. So for example, in here, we wanted to optimize the model for best long-term predictions. So it's learning abstractions that can give out this. But if we add some sort of, I don't know, policy network over it and try to do some optimal control, rewards and try to think about optimal behavior, then the sort of abstractions it might learn maybe something different. I don't know. But yeah, I think, yeah, it's learning something based on this loss function right now. Some sort of, but I haven't tried to visualize it or something like it should be done, I would say.
Is the right way to think about it that it's just like it's compartmentalizing whatever information can be compartmentalized into this abstract state that's like neat, that's like it's more of like an information representation that's the most
what is
efficient
important for long-term predictions.
Exactly.
Only those information and then leave the
Okay.
details or something like that. So, but that's based on the loss. So if we
Yeah.
try different laws, maybe it learns some other stuffs. What is important for that particular task or something like that.
Because it like when I'm thinking about the choice of H, like yes, you've done this nice sensitivity analysis over H, but in the case of another system that really does have like sort of fundamental dynamics changes or whatever, there is like a right choice of H. Like you want that H to match where your dynamics is actually going through, like switching modes or something like that or something, right? But so in this case, do you think it would be possible to just like, could you also optimize over H like directly inside your optimization and just
So what kind of task changes maybe like?
Well, so like I could imagine that if you had like a dynamical system that actually had like distinct modes, I'm imagining like let's say even something like a humanoid robot or anything where there's contacts, where like there's like a distinct change in the dynamics based on some kind of discrete variable. So it would make maybe some sense in that case to like actually switch your lower level abstraction to be aligned with the transitions in the discrete transitions in your like actual underlying dynamics. That's not exactly what's happening here, but would be nice, right?
So I don't know if it can model this exogenous changes, like changes coming from external factors, like some contact suddenly coming and the sudden stuff. So maybe it cannot, but let's say it remains fixed for a certain set of like the discrete task remains fixed for a certain time period, then this H remains fixed over a certain set periods, something like that. That can happen. But what if it the H varies, like the task varies within that H time steps or something like that? Then I think maybe you have to carefully choose the H to add more hierarchies like
Yeah.
have smaller edges and then add another hierarchy with a larger edge, and then increase this resolution in a hierarchical way, which may help.
Makes sense.
You had a table, I think it was like where you set H's and you put them in seconds. It's like, I think some of them are 2.5, some of them are 6. I was curious how you chose those. Did you like do like the analysis where you
So this was the maximum available from those sources, many of this. So for example, I think for the
yeah, is it horizon the same page that you plan on?
Sorry?
So there's the table, I think a few slides forwards where you had like prediction horizon. That's the same as your H?
I can't hear you well. Can you please repeat?
You had a table and then the first column was task and the column was like prediction horizon. And it was like the first row was like 2.5 seconds. Oh yeah, the slide. The last slide that you just showed.
This one, yeah, okay, yeah.
Is the prediction horizon the same as your H?
No. So the prediction horizon in most cases is around, so for a 2-level hierarchy, it's around 0.3 to 5 seconds. So that's the edge. The edge is chosen as 0.3 to 5 seconds. So it varies. So the number would vary depending upon the frequency at which the data is collected. For example, in case of let's say the mobile robot, the data was collected at 250 hertz, and 0.3 seconds would be around 75 steps. So that's the edge in case of mobile robot. Here it was collected at 100 hertz, and yeah, it was 0.3 seconds is 30. So that was the edge that was chosen. And that's what we observed. Around 0.3 to 0.5 was somehow making sense for this prediction task, at least. But yeah, this is the maximum possible long horizon prediction that you have to do. The trajectory length, that's what is mentioned.
I guess in terms of time scale.
Sorry?
So your H was relatively consistent. You didn't have to choose it that much in terms of like.
So this is a very interesting thing. So like, so initially when we submitted the paper, we chose this like 0.3 seconds is a reasonable assumption some of the previous papers made in which you can assume the dynamics can be assumed to be a constant. So that's why we chose this 0.3 seconds for almost all the stuffs. But then this study was asked by the reviewers. So that's when we did it. And for some reason, that was also making sense. Like the 0.3 seconds were like around that region was the most best edge value. But I did the study only for the hydraulic excavator and the mobile robot, and maybe also Franca kitchen. So I don't know if we change this edge to something other than 0.3 seconds for this maze or something like that. Maybe the prediction improves or decreases or something like that. So yeah, so this is the 0.3 seconds I got from this meta-learning literature, like meta-learning model-based literature, where they assume that, yeah, for 0.3 to 0.5 seconds, you can assume that the dynamics won't change too much. If it's a continuous dynamical system, it won't be like drastic changes. So this is a reasonable assumption to make.
I see. Okay, thank you.
Yep. Okay, any more questions?
All right, well, if there's no more questions, I think you put your email at the very end. So if we have any more follow-ups, we can email you there.
Yep.
Okay, perfect. Yeah, so let's wrap it up. Thanks again for coming and giving you a great talk. Yeah, and thanks everyone for coming.
Thanks so much.
Thank you for the opportunity. See you then. Have a good day.